Preparing for a Databricks Data Engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. What is the Databricks Lakehouse, and why would you choose it over a traditional data warehouse? The Databricks Lakehouse combines the flexibility and low cost of a data lake with the governance and performance expected from a warehouse. I would choose it when an organization needs one platform for raw files, curated analytics, machine learning, and streaming. Delta Lake supplies reliability, while SQL warehouses and optimized execution support BI workloads. This reduces duplicate pipelines and data copies. The key business benefit is a governed, reusable data foundation rather than separate silos. While answering, focus on the Lakehouse architecture, unified batch and streaming workloads, open storage formats, governance, scalability, reduced data movement, and how Databricks combines warehouse performance with data lake flexibility. Question 2. How does Delta Lake provide ACID transactions on cloud object storage? Delta Lake adds a transaction log beside Parquet data files. Each successful write records an atomic commit describing added, removed, or changed files, allowing readers to construct a consistent snapshot. Optimistic concurrency detects conflicting updates before committing. This provides atomicity and isolation even though object storage does not behave like a traditional database. I also use schema enforcement and time travel to prevent accidental corruption and recover or audit earlier table versions. Make sure to cover the transaction log, optimistic concurrency, atomic commits, snapshot isolation, schema enforcement, time travel, object storage limitations, and how readers identify the latest consistent table version. Question 3. Explain the difference between managed and external tables in Databricks. A managed table has both metadata and data controlled by the catalog, with storage placed in the configured managed location. Dropping it generally removes the underlying data. An external table stores data at a location managed outside the catalog, so dropping the table usually removes metadata but preserves files. I prefer managed tables for platform-owned datasets and external tables when storage lifecycle, cross-platform access, or regulatory ownership must remain independent. In your answer, distinguish ownership of data and metadata, storage locations, drop behavior, lifecycle management, migration implications, access controls, and when external tables are preferable for shared or independently governed data. Question 4. What is the Medallion architecture, and how would you implement it? Medallion architecture organizes data into bronze, silver, and gold layers. Bronze preserves source data with minimal transformation, silver standardizes types, removes duplicates, and applies quality rules, while gold serves business-specific reporting or machine learning use cases. I would make each layer incremental, testable, and auditable, retaining source metadata for replayability. I would not create layers mechanically. The design should improve ownership, quality, lineage, and consumption rather than add pipeline complexity. Be sure to mention bronze, silver, and gold layers, progressively refined data, raw data preservation, quality rules, business-ready aggregates, replayability, lineage, and avoiding unnecessary layers when requirements do not justify them. Question 5. How would you design an incremental ingestion pipeline for files arriving in cloud storage? I would use autoloader with a checkpoint location and a delta target. It tracks discovered files so reruns do not process the same input repeatedly, and I would configure schema evolution carefully, routing unexpected fields to rescued data when appropriate. The pipeline would add ingestion timestamps and source file metadata, validate records, and quarantine malformed inputs. Checkpointing, metrics, alerts, and replay procedures are essential because ingestion reliability matters as much as transformation logic. Focus on autoloader, checkpointing, schema evolution, rescued data, exactly once behavior, idempotent writes, file notification modes, late arrivals, and operational monitoring for failed or malformed files. Question 6. What is structured streaming, and how do you guarantee reliable processing? Structured streaming lets me express continuous processing using data frame and SQL APIs while Spark manages incremental execution. For reliability, I configure durable checkpoints, use a transactional delta sync, and make transformations deterministic. Watermarks bound state for late data, while output modes control how results are written. I also verify the source and sync semantics. Exactly once processing is strongest with delta, but external systems may require idempotent keys or transactional integration. Cover sources and syncs, micro batches, checkpoints, output modes, watermarks, trigger intervals, fault tolerance, ID impotency, state management, and the distinction between practical exactly once guarantees and external system limitations. Question 7. How do watermarks handle late arriving data in a streaming pipeline? A watermark uses event time to indicate how long the engine should retain state for late records. For example, with a 10-minute watermark, Spark can update a window while records arrive within that delay, then eventually evict state and finalize older windows. This limits memory growth. Records arriving beyond the threshold may be dropped from the aggregation, so I choose the delay based on observed lateness and business tolerance, then monitor late data metrics. Explain event time versus processing time, watermark thresholds, state cleanup, late record treatment, windowed aggregations, trade-offs between completeness and memory, and what happens to records arriving beyond the configured threshold. Question 8. What causes small file problems in Delta Lake, and how would you solve them? Small files usually result from frequent micro-batches, over-partitioning, or many concurrent writers. They increase metadata overhead and force readers to open many objects. I would reduce unnecessary partition columns, enable optimized writes or auto-compaction where suitable, and schedule optimize for existing tables. I would also review trigger frequency and workload patterns. The goal is not simply larger files, it is a balanced design that preserves ingestion latency while improving scan efficiency. Mention frequent streaming writes, excessive partitions, file size targets, optimized writes, auto-compaction, optimize, partition strategy, liquid clustering where appropriate, and balancing write latency against read performance. Question 9. How do you optimize a slow Spark job running on Databricks? I start with the Spark UI and explain plan rather than changing settings blindly. I look for large shuffles, skewed tasks, unnecessary scans, spills, and repeated computation. Then I apply predicate and column pruning, choose appropriate join strategies, repartition only when justified, and address skew with salting or adaptive execution. I inspect delta file layout and cluster sizing afterward. Finally, I benchmark before and after, because optimization must improve measured runtime without creating unsustainable cost. In your answer, discuss Spark UI diagnosis, execution plans, shuffles, skew, partition sizing, predicate and column pruning, join strategy, caching discipline, file layout, cluster configuration, and measuring improvements with representative data. Question 10. What is data skew in Spark, and how would you address a skewed join? Data skew occurs when a few keys hold a disproportionate share of records, causing certain partitions and tasks to run much longer than others. I would confirm this through task durations and partition statistics in the Spark UI. Depending on the case, I might enable adaptive skew handling, broadcast a genuinely small dimension, pre-aggregate, or salt hot keys and replicate matching dimension rows. I would validate results carefully because salting changes join mechanics and can introduce duplicates. Make sure to cover uneven key distribution, long-running tasks, identifying skew through Spark UI, adaptive query execution, salting hot keys, broadcasting small tables, pre-aggregation, and validating that the fix preserves correctness. Question 11. When would you use a broadcast join in Databricks? I use a broadcast join when one side is sufficiently small to fit safely in each executor's memory. Spark sends that table to workers, avoiding a shuffle of the larger dataset and often reducing runtime significantly. I check actual size, not just row count, and review the physical plan to confirm the strategy. A broadcast hint should be deliberate. Broadcasting an unexpectedly large or wide table can cause memory pressure, failures, or slower execution. Discuss small table size relative to executor memory, avoiding shuffle, broadcast thresholds, executor pressure, stale statistics, forced hints, repeated reuse, and the risks of broadcasting a table that is too large. Question 12. How would you implement data quality checks in a Databricks pipeline? I define quality rules close to the transformation layer, covering required fields, valid ranges, uniqueness, referential integrity, and freshness. Depending on severity, a rule may fail the pipeline, quarantine invalid records, or emit a warning. I record pass, fail, and quarantine counts with pipeline metadata, then alert owners when thresholds are breached. Expectations should be version controlled and reusable. A successful pipeline is not merely one that finishes, it produces trustworthy, explainable data. Focus on expectations, null and uniqueness checks, referential integrity, quarantine versus failure policies, audit metrics, alerting, reusable tests, thresholds, and making quality outcomes visible to downstream consumers. Question 13. What is Unity Catalog, and how does it improve governance? Unity Catalog provides centralized governance for Databricks data and AI assets. It organizes objects into catalogs, schemas, and tables, then applies permissions consistently using groups and service principals. I would use external locations and storage credentials to control cloud access rather than embedding keys in notebooks. Its lineage and audit capabilities improve impact analysis and compliance. For sensitive datasets, I would add row filters, column masks, and least privilege access aligned with ownership. Cover centralized metadata, catalogs, schemas, tables, fine-grained permissions, lineage, auditing, external locations, managed identities, row and column controls, and separation of duties across workspaces or teams. Question 14. How do you manage schema evolution in Delta Lake safely? I distinguish additive changes, such as a nullable column, from breaking changes, such as renaming or changing a type. I keep schema enforcement enabled by default and allow evolution only through reviewed, tested deployments. For controlled additions, merge schema or auto-merge may be appropriate, but I avoid enabling them broadly because unexpected fields can silently affect consumers. I publish schema versions, test downstream queries, and use migration or backfill plans for incompatible changes. Explain additive versus breaking changes, schema enforcement, controlled evolution, merge schema or auto-merge risks, compatibility testing, rescued data, versioning, downstream communication, and rollback or migration procedures. Question 15. Explain Delta Lake merge and describe a common pitfall. Merge combines insert, update, and delete logic by matching source and target keys. I use it for CDC upserts, for example updating an existing customer and inserting a new one-in-one transaction. A major pitfall is duplicate source keys, which can produce ambiguous matches or incorrect outcomes, so I deduplicate using business keys and change sequence before merging. I also include audit timestamps and test delete behavior, late updates, and reruns for ID impotency. Mention matching conditions, inserts, updates, deletes, upserts, source uniqueness, duplicate matches, ID impotency, partition pruning, audit columns, and handling late arriving changes without unintended overwrites. Question 16. How would you process CDC data in Databricks? For CDC, I preserve the source operation, primary key, and ordering metadata in bronze. In silver, I deduplicate events by key and sequence, then apply inserts, updates, and deletes through Delta merge or a carefully designed streaming process. If available, change data feed helps downstream consumers capture table changes efficiently. I retain tombstones and checkpoints because replayability matters. The critical correctness issue is applying changes in source order, not merely arrival order. Be sure to cover operation codes, ordering by sequence or commit timestamp, deduplication, deletes, tombstones, change data feed, streaming checkpoints, merge logic, replayability, and handling out-of-order events. Question 17. How would you use Databricks Workflows to productionize a data pipeline? I would create a multitask workflow with explicit dependencies between ingestion, transformation, validation, and publishing tasks. Parameters make the same code reusable across environments, while retries handle transient failures without hiding persistent defects. I configure alerts for failures, duration, and quality thresholds, and use task values for controlled handoffs. Production jobs should run versioned code with service principal permissions. I also design repairable tasks so operators can restart from a failed stage safely. Discuss job tasks, dependencies, parameters, retries, alerts, schedules or event triggers, task values, environments, permissions, repair runs, observability, and separating development notebooks from deployable production code. Question 18. What is the difference between job clusters, all-purpose clusters, and SQL warehouses? Job clusters are created for a run and terminated afterward, which improves isolation and cost control for production pipelines. All-purpose clusters support interactive development and collaboration but can remain idle and become expensive. SQL warehouses are optimized for SQL analytics, dashboards, and concurrent by users, with their own scaling behavior. I use job clusters for scheduled engineering workloads, all-purpose clusters during development, and SQL warehouses for governed analytical consumption. Compare lifecycle, cost, isolation, collaboration, workload type, startup behavior, autoscaling, governance, concurrency, and when each option fits engineering jobs, interactive development, or SQL and BI workloads. Question 19. How would you troubleshoot a failed Databricks job in production? I first identify the failed task, error class, run parameters, and whether the failure is deterministic or transient. I review driver and executor logs, Spark UI stages, input availability, schema changes, and recent deployments. If safe, I rerun the task with the same parameters, avoiding blind full pipeline retries that may duplicate outputs. After restoring service, I document root cause, add a regression test or alert, and improve ID impotency or capacity if those contributed. Focus on identifying the failing task, reading driver and executor logs, checking recent code or schema changes, inspecting Spark UI, validating input availability, assessing retries and data quality, and documenting the root cause and prevention. Question 20. Describe a Databricks data engineering project you would be proud to discuss in an interview. I would describe a pipeline that ingested roughly 2 terabytes of daily events, transformed them through bronze, silver, and gold delta tables, and served operational dashboards. I owned the incremental design, quality checks, workflow orchestration, and performance tuning. By reducing small files, pruning columns, and optimizing joins, I cut runtime from 3 hours to 45 minutes while lowering compute cost. I would also explain one production failure, how we recovered, and the controls added afterward. In your answer, structure the story around business problem, scale, architecture, personal contribution, quality and governance, performance or cost results, trade-offs, production incident learning, and measurable outcomes. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.